Good morning friends, welcome again all of you to my video channel on structural design. Today we will continue the same problem what we have already started in the last video, the design of one-way slab. A problem is given to design a slab for a room of size 4 meter by 10 meter, isn't it? The same question, 4 meter by 10 meter, the shorter dimension 4 meter, the larger dimension 10 meters. Okay, and we have completed the first 6 steps, including the checking of the effective depth required for the slab. The wall thickness was given as 230 mm and the material properties Fe 415 steel and FCK 20 Newton per mm square. Okay, now the next step, 7th one, to find out the area of steel required, area of main steel AST. Area of main steel AST is to be calculated. So you know the formula to find out the ultimate moment of resistance of the beam. The same formula we can use it here. Mu is equal to 0.87 Fy AST Fy AST into D into 1 minus Fy into AST divided by FCK BD. Okay, the same formula what we have used for the beams. Now here we already calculated the value of Mu, we know the value of Fu, we know the effective depth D, and we know FCK 20 Newton per mm square, Fy 415, B 1000 mm, and effective depth also we have calculated. Okay, substituting all these values, find out the value of area of steel required, right? Area of tension steel required. That is, when you substitute this one, you will get AST is equal to 558.15 mm square. 558.15 mm square as the area. It's a quadratic, you will get a quadratic equation. Then by solving, you will get 2 answers. Take the required value, right, for the AST, 558. Out of the 2 values, the admissible value you can take as 558.15 mm square. Now, as per the code SP 456, when you refer page 48, you can see the minimum reinforcement, minimum tension reinforcement, AST minimum for the slab, AST minimum. That means minimum area of tension reinforcement is equal to 0.12 percentage, 0.12 into 100 into gross area. That is given in page 48. Okay, for HYST bars, it is 0.12 percentage of the gross area. What is the gross area? That is B 1000 into 185 mm is the effective depth, isn't it? BD, sorry, not the effective depth, the overall depth, BD. So it is 0.12 percentage of AG, gross area. What is gross area? Gross area is 1000 into 185, the breadth into overall depth. So calculate this minimum AST, that is equal to 222 mm squared. You get the value as 222 mm squared. So the area of steel should not be less than this one, but we got it as 558.15. Therefore, take the area of steel as 558.15 mm square. Area of main steel in the slab. Now, we have already assumed 10 mm dia bars, isn't it? 10 mm dia bars. So, provide 10 mm dia bars, right? Provide 10 mm dia bars as the main steel. Then we have to find out the spacing. How to find out the spacing? There are 3 provisions to find out the spacing. Out of that, take the minimum value. What are the 3 provisions? 1, SC is equal to what? You know area of one bar, the diameter of the bar is 10 mm. So what is the area of one bar? Let it be, say, small AST divided by total area is capital AST into what? Into the breadth, that is 1000. So that will be the spacing, isn't it? Area of steel of one bar, the total area of steel into 1000. So area of one bar is equal to pi by 4 into 10 squared divided by, this is 558.15 into 1000. That is the spacing. Okay, that's equal to 140.17 mm, the spacing of the bars, 10 mm dia bars. Now the second provision, what is this? S is equal to 3D. That means 3 times the effective depth of the slab, equal to 3 into, what is the effective depth? 160, isn't it? Is equal to 480 mm. The second value, and the third value C 300 mm. So these are the 3 provisions as per the code IS 456. So refer page 46, 47 and 48, right? These 3 pages you will get the spacing and also the percentage of reinforcement also that is given here, AST minimum. This is from page 48, this one page 46 and 47. Okay, so A 140.17, B 480 and C 300 mm. So out of this provide the minimum 140.17, 144.17, therefore provide 10 mm dia bars, 10 mm dia bars at 140 mm center to center. So the design of steel reinforcement is over, main reinforcement. Provide 10 mm dia bars at 140 mm center to center. Isn't it the main steel? Now, similarly, number 8, area of distribution steel, ASTD distribution. How to find out the distribution steel? You know, the distribution steels are also provided in the slabs to take the temperature stresses for the shrinkage, to reduce the shrinkage, or to distribute the loads on the slab. Usually distribution steels or temperature reinforcements are provided in addition to the main steel. How to find out it? That is from the code. As per the code, we know the minimum reinforcement, that is 0.12%, the same thing, 0.12 percentage of the gross area. The gross area is the same thing, that is 1000 into 185. 1000 into 185 is equal to 222 mm squared. That is the area of distribution steel, right? Then here, when we assume, so main reinforcement assumes a 10 mm diameter. Now distribution steel, usually the diameter will be less than the main reinforcement, so we assume 8 mm dia. 8 mm dia bars as the distribution steel. Then find out the spacing. S is equal to AST, small AST pi by 4 into 8 squared divided by AST is equal to 222 into 1000. Isn't it? Is it clear? Here for the main steel we have taken AST by AST into 1000, where this AST was the AST of the main reinforcement, that we got it as how much? 558.15. Here the AST for the distribution steel, that is equal to how much? Pi by 4 8 squared by 222, isn't it? By 222 into 1000 is equal to how much? S is equal to pi by 4 into 8 squared divided by 222 is equal to 226.42 mm the spacing. And B, what is it? The second provision for the distribution steel, it is not equal to 3D, that is 5D for distribution. Remember, for main steel spacing 3D, Here it is 5D equal to 5 into, what is the value of D? 160 is equal to how much? 800 m. 800 mm, and the third one the same thing, 300 mm, the main spacing. Right? Okay, 800 mm, and the third C, sorry, not 300, that's for main steel, 450 mm, sorry, 450 mm. So for distribution steel, what are the three provisions to get the spacing? First one, find out the spacing taking AST by AST into B, 1000. Small AST by capital AST into 1000, that is one value. Second value, 5 times the effective depth, 5 into 160, 800 mm, and third one, 450 mm. Out of this, take the minimum value. So provide 8 mm dia bars at 226 mm center to center. Okay, 226 or 230, you can say, assume 230 mm center to center approximately. So the design of main and distribution steels are over. Main steel, 10 mm dia bars at 140 mm center to center, and distribution steel, 8 mm dia bars at 230 mm or 220 mm center to center. 226 you can round it to the nearest small value, 220. See, instead of taking 230, take it as 220 mm center to center. When we round it, approximately 220 mm. So these are the diameter and spacing of main and distribution steel. Now the next step, so after calculating the main and distribution steels for the slab, now what is the next step? We have to check. Number 9, check for shear. Check for shear. Check for shear. The method is the same as that of the beam. You know what is the first step? To find out the nominal shear stress, tau v, isn't it? Tau v is the notation for the nominal shear stress. That's equal to what? Vu divided by Vd, the maximum shear force, by B into D. Right? We have already calculated the maximum shear force. It's equal to 28.76 kilonewton or into 1000 newton divided by, what is B? B is equal to 1000 into D is equal to 160. Right? That is tau v. The same thing as we have done in the beam. Vu by Bd is equal to 0.179 Newton per mm squared. Newton per mm squared tau v. Then what's the next step? Find out the design shear stress, tau c. For that we need what? Percentage of reinforcement Pt, that's equal to 100 AST by Bd. Right? 100 AST divided by BD, that is 100 into 558.15 divided by 1000 into 160. This is the effective depth, 160 is equal to how much? Is it clear? 100 into AST divided by B into D. Right? That is the value of that's the value of percentage of reinforcement is equal to 0.348. Now we got the value PT 0.348, and from the table, as we have already done for the beam, find out the value of tau c. Right? The value of tau c, that's equal to 0.4 Newton per mm square. You'll get it from the table, 0.4 Newton per mm square. Now we check. Tau b is equal to 0.179. Tau c 0.4. So design shear strength is 0.4, the other one is 0.179. Therefore it is safe. The slab is safe against shear. Against the shear. So it can go up to 0.4, but as per the load, the maximum shear force in our slab, it is only 0.179. Therefore it is safe. Okay, the slab is safe against shear. So that checking is over. And the last one, number 10, check for deflection. That's the last step. Check for deflection. How can we check for deflection? I told you already, the deflection is the measure of stiffness of the beam. That means the ratio between the effective span and effective depth, span by depth ratio, right? Span by depth ratio. That means L by D calculated and L by D proposed. We have to check these two. L by D calculated should be less than what? Should be less than L by D proposed. Isn't it? So therefore, L by D calculate, how can we calculate this L by D ratio? We know L by D, L is equal to how much? Effective span, we already calculated now, 4160 mm, that is the calculated one divided by D is 160, isn't it? L by D ratio, that's equal to 26. As per the effective span and the effective depth, the ratio, L by D ratio is 26. Now, what is the next L by D proposed? L by D, that is equal to what? L by D proposed is equal to, as per the code, it is basic value into modification factor. We can find out that L by D, to check the deflection, multiply the basic value with the modification factor. Basic value, I told you in the last class, it is for simply supported beam or slab, that's equal to 20. The value is 20, basic value, isn't it? It is 20. Then, what about the modification factor? To find out the modification factor, we have to find out as per the value of PT. PT we already calculated the percentage of reinforcement, 0.348, isn't it? PT is equal to 0.348. Fs is equal to Fs. That means from the code IS 456 in figure 4, check in figure 4 that graphs is according to this PT, that means percentage of steel, and the Fs value. What is Fs? Fs is equal to 0.58 into Fy. What is Fy? Fy is the yield strength, that is 415.458 into 450. That is the Fs value. So calculate that Fs value, that's equal to 240. It will be by multiplying this 240. So based on this 240 and PT value 0.348 from the figure 4, you will get the MF value, the modification factor. MF means modification factor 1.4 from the graph. So check that from the code, it is 1.4. Therefore, L by D is equal to how much? Now, therefore, this L by D will be, L by D post is equal to how much? That's equal to this value, modification factor 1.4 and the basic value 20 into 1.4, that's equal to how much? 28, the ratio 28. So previously we got the ratio 26, this one 28, is less than 28, and therefore the deflection criteria also safe against deflection. Our slab which is safe against deflection. So calculate L by D ratios, both L by D ratios, and compare here for the checking of shear. Calculate the nominal shear stress and the design or the maximum shear stress and compare. So from these two you will get the checking for shear and deflection, right? So these are the 10 steps to design a one-way slab. isn't it? So I think all of you remember the steps. The first step, select the type of the slab, whether it is one-way slab or two-way slab. Right? As per the ratio, Ly by Lx, whether it is greater than 2 or less than or equal to 2. Right? Then number 2, calculate or assume the effective depth and overall depth as per the criteria. We have seen that in the last video. And the third one, effective span Le from the criterias, taking clear span plus effective depth or clear span plus 1 wall thickness. Then after that, calculation of the loads. The loads includes dead load, live load and floor finish. Add these 3 and find out the factored load by multiplying with 1.5. After calculating the loads, the factored load, calculate the maximum BM and maximum SF. Maximum bending moment and maximum shear force. Once you obtain the maximum bending moment and maximum shear force, the next step to check the effective depth required. The effective depth required and compare with the effective depth what you have assumed. Then next step is both the areas of steel, area of main steel and area of distribution steel. 7 and 8, 9 and 10, checking for shear and checking for deflection. Okay, these are the 10 steps to be followed while designing a one-way slab. It's okay. I think it's clear to all of you. Again, you will see in the next video. Okay, thank you one and all.